Okay, part two. So this is the follow-up to our inductive reasoning one. And this is all about disproving things. So through inductive reasoning and through conjectures, we can make good guesses about things, but it's really, really hard to prove something is true, like we talked about last lesson. But luckily for you guys, it's actually much easier to disprove something than it is to prove something. Disproofs are much, much easier to perform. And these, all you need to do to disprove something is find a counterexample. So learn to invalidate a conjecture by finding a contradiction or a counterexample. A counterexample is an example where the rule does not hold. That's it. If you can find any example where the rule does not hold true, then the rule is broken. The rule does not work. Okay, so try this with your partner. Some really easy ones at the beginning, but pause, take like 4 minutes, do it really, really quick. Just say no, example, and give me your counterexample. Okay, hopefully you had a chance to do that. If you live in a country bordering the United States, then you live in Canada. No, example, you could be living in Mexico. Hopefully your geography is up to scruff, is the expression. If a quadrilateral has 4 right angles, then it must be a square. No. Example. You could draw it or you could name it. I think it's more effective if you draw it. There are such things as rectangles, which still contain 4 right angles, but is not a square. Odd whole numbers less than 10 are prime. Are they all prime? Well, 1, let's look at them all. So there's 1, 3, 5, 7, 9 are our odd whole numbers less than 10. Is 1 prime? That's actually tricky. This one I would leave it out for my proof. Most people say no, it is not prime, because the definition of prime is it can only be divided by itself and 1. So most people consider 1 like the throwaway number, where it's not really prime and it's not really not prime, it's just necessary at the beginning. So let's ignore that one, because that could be tricky. Is 3 prime? Yes. Is 5 prime? Yes. Is 7 prime? Yes. Is 9 prime? No. So there's our counterexample. 9 is equal to 3 times 3. So 9 can be divided by 1, it can be divided by 9, and it can be divided by 3. Counterexample. All birds can fly. No way. Example. I wonder what Austin got. The only one I know of is penguin. Okay, let's try a couple more. Consider this conjecture. So they do get a bit harder than this, but that's the general idea. This is the idea in the world. Now we're going to do it more mathematically. The sum of 2 prime numbers is an even number. Give 2 examples for which the conjecture is true. 3 plus 5 is equal to 8. That's true. 5 plus 13 is equal to 18. True, true. 2 prime numbers, their sum is indeed an even number. Now give 1 counterexample which proves this not true. Think about this one for a second. If you remember, if you're smart, you remember from this last lesson that we said every 2 odd numbers is going to equal an even number when you add them together. Now, sorry, my speaker's kind of freaking out. So now we can think every prime number, almost every single prime number is odd. every single prime number after 3 has to be odd, because if it's even, it divides by 2. So none of those ones we're going to find a counterexample in. Every single pair of odd numbers is going to make it even. But the counterexample is going to be something with 2, because 2 is prime. So add 2 to any number, that's also prime. And we've got our counterexample. An even and an odd one is odd. So not every 2 prime numbers add to an even number. Almost every 2. It really has to include the 2. That's the only way to get a counterexample. Okay. Matt found an interesting number pattern. 1 times 8 plus 1 equals 9. 12 times 8 plus 2 equals 98. 123 times 8 plus 3 is 987. 1, 2, 3, 4 times 8 plus 4 is 9876. Interesting. Is this relationship going to hold? Let's try out a couple. So they said that's 9876. Let's try a couple more. So the next one is going to be 1, 2, 3, 4, 5 times 8 plus 5. Calculators out. I get 9, 8, 7, 6, 5. Okay, still holds. Let's try the next one. 1, 2, 3, 4, 5, 6 times 8 plus 6. I get 9, 8, 7, 6, 5, 4. Huh. So we're searching for a counterexample. We're not sure if this is still true. Let's just try 2 more. Let's not do 9 and 10. We're going to get huge. But try 2 more, see what you get. Okay, well, for the first 8 numbers, it seems to hold true. So we don't know how long to look for a counterexample if it's a really hard relationship, but you should try a bunch, especially if you think the relationship isn't true. This one is quite hard, so I don't know if we can tell just by looking at it whether or not we think it's going to be true or not. It seems to be true. I don't know what happens after 10 and 11, so I might want to jump a couple. Let's try 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I had actually 2 digits there. Times 8 plus 10. I get 9, 8, 7, 6, 5, 4, 3, 1, 2, 9. Oh, it breaks. So it actually breaks at 10. That's why they bolded this number. The relationship, nothing seems to change as long as it's single digits, but as soon as you add 2 digits to the end, it actually does break. So this is kind of good for a couple reasons. A, you're not sure how long to look for counterexamples, but you should try to test it in certain ways that you think will break it, especially if you think it can be broken. You might need to use your intuition. And you want to check funny numbers. So don't just keep going down the line if it looks like it's going to hold. Maybe jump to 10, see if 10 still holds, because now all of a sudden something new is happening. We now have 2 digits. So it does actually break at 10. So you can't trust just a group of numbers to prove that it's true all the time. This pattern will break, but it's still true for all the single digits, which is pretty good. Okay, Give two examples that support each conjecture and one counterexample that shows it's false. The sum of two perfect squares is an even number. What is a perfect square? That's one of our purple numbers up there. The sum of two of them is an even number. Well, 4 is one of them, and 64 is one of them, which makes 68, which is indeed even. I also have 9 as one of them, and I also have 49 as one of them, which equals 58, if I did that right, which is also an even number. So 2 ways to prove it's true, 1 way to prove it's not true. 4 plus 9 is not going to be an even number. So we seem to be coming back to that same rule. 2 evens make an even, 2 odds make an even, but 1 of each is how you get to an odd number. The square root of a number is smaller than the number. Isn't that always true? Well, what's the square root of 4? That's 2. What's the square root of 9? Well, that's 3. So true examples are easy. If you square root a number, you're always going to get something smaller. Find a counterexample. I actually want you to think of this. This is actually going to be a good test for you guys. So pause this, take however long it takes, play around with your calculator, find a counterexample. I'm going to restart at 12. Okay, so you probably, hopefully your intuition can tell you if I go bigger, it's not going to do anything. Square root of 100 is 10, so it still works. So what if I go smaller? Well, I could try the square root of -4, but that is broken. We can't actually go into negative numbers. That's not allowed. But there's some other numbers we could try. And now there's 3 places you could find counterexamples. You could have done the square root of 0, you could have done the square root of 1, or you could have done the square root of any number between 0 and 1. So these are where our counterexamples are, really small numbers that are still positive. Because the square root of 0 is 0, square root of 1 is 1, and the square root of any number between 0 and 1, like 0.5, what is the square root of 0.5? Root 0.5. Oh, it's bigger. Our fractions are actually bigger when you square root them. These two numbers are the same, and anything between them is actually bigger. So that's our counterexample. All 3 of these would work, actually, because they said it's always smaller than. They never said anything about equal. So counterexamples. Okay, lots of homework questions. You still have lots of time. So please, if you need to take like a 3-minute break, calm down. You can, but you have to try a whole bunch of examples and make sure you're ready. We probably should do a quiz on this already tomorrow. Okay, good luck.